This content is produced by Pass the CSLB, an independent educational channel. I am not a licensed contractor, attorney, or engineer. This is exam preparation material only, based on publicly available CSLB study resources. Nothing here constitutes legal, professional, or engineering advice. Exam content is set by PSI and the CSLB and may change. Always verify current requirements against official CSLB materials. I cannot guarantee any exam outcome. Now let's get into it. This episode covers everything you need to know about cutting, notching, and boring structural wood framing members, floor joists, wall studs, top plates, and roof rafters. The governing code sections are California Residential Code R502.8 and R802.8.1 for floor joists, R602.6 and R602.6.1 for wall studs and top plates, and R802.7 and R802.7.1 for roof rafters. Official preparation resources consistently identify this as a priority area for the General B trade examination, and once you understand why these numbers exist, you will own them permanently. Why these rules exist: the physics of structural load. Before I give you a single number, I want to give you the physics behind every number in this topic. Because if you understand why each rule exists, the numbers stop feeling like something you have to memorize and start feeling like the only answer that makes sense. That is a completely different relationship with material under pressure, and it is what separates people who pass on the first attempt from people who blank out with 40 questions left on the clock. When a floor joist spans between two supports and carries a load from above, it behaves as a simple beam in bending. I want you to picture this clearly. Take a wooden ruler and hold it flat between two stacks of books. Now press down in the middle. The top surface bows inward. It is being compressed, fibers crushed together. The bottom surface bows outward. It is being stretched, fibers pulled apart. That is bending. And in a beam carrying a uniform load, the bending is not equal along the entire span. It builds from zero at each end and reaches its absolute maximum right at the center of the span. This is the most important structural fact in this entire episode. The wood at the center of the span is working harder than anywhere else in that member. It is under maximum compression on top and maximum tension on the bottom simultaneously. That is where the joist will fail first if you weaken it. And this is precisely why the code draws a hard boundary around the middle 1/3 of every floor joist span and declares no notches, 0, not a reduced limit, not a smaller fraction, 0, with no exceptions, no conditions, and no partial allowances of any kind. The story of how these limits became codified is worth knowing. Before standardized framing codes became widespread in residential construction, tradespeople would route pipes, wires, and ducts through floor joists however they found convenient. There was no universal standard. A plumber would notch wherever the pipe needed to go. An electrician would bore through whatever was in the way. Buildings were framed, systems were installed, and years later, sometimes decades later, floors would show excessive deflection under normal loading. Structural investigators repeatedly found unauthorized framing modifications as contributing factors. The engineering community studied the failure patterns, and the specific fractions we use today represent the threshold below which a modified solid sawn member still performs within its design intent. These are not conservative guesses. They are empirically derived structural limits. Now let me tell you about shear, because it explains the end-notch rule. Shear stress, the force trying to vertically slide one cross-section of the joist past the adjacent one, is distributed in the opposite pattern from bending. Shear is maximum at the ends of the member at the bearing points and drops to 0 at midspan. Because bending is near 0 at the ends, the code tolerates a deeper cut there. That is the end notch, permitted at the bearing point, because bending failure is not the risk at that location. But even the end notch has a hard limit. Bored holes are governed by a third principle. When you drill through the approximate center of a joist's depth, you are removing material near the neutral axis, the imaginary horizontal line through the middle of the section where compression becomes tension and net stress is 0. Material near the neutral axis carries less stress. This is why holes can be proportionally larger than notches. But drill that hole close to the top or bottom edge, and you are removing material from the highest stress fibers in the cross-section. The mandatory 2-inch clearance from any bored hole to the top or bottom face of the joist protects exactly those fibers. Vertical wall studs operate on completely different mechanics. A bearing wall stud is a column in compression. It carries the cumulative weight of everything above it and transmits that load downward. Columns fail by buckling, and buckling is not a gradual process. A column holds its full load until the instant it does not. When you notch a bearing stud or bore a large hole through it, you reduce the cross-sectional area available to resist that compressive load. The bearing wall stud rules are deliberately tight because the consequences of getting them wrong are sudden and catastrophic. Floor joists, the 3. Governing fractions for solid sawn lumber floor joists. California Residential Code R502.8.1 establishes 3 governing fractions that control every modification to the member. I teach these as a set using 3 words: holes, notches, ends. Holes. The maximum diameter of any bored hole is 1/3 of the member's actual depth. Notches. The maximum depth of a notch cut into the top or bottom of the joist, located in the outer thirds of the span, is 1/6 of the actual depth. Ends. The maximum depth of an end notch at the bearing point is 1/4 of the actual depth. The sequence is 1/3, 1/6, 1/4. Holes get the most room, 1/3, because a bored hole leaves intact material on all 4 sides of the penetration. Span notches get the least room, 1/6, because they exist in zones with real bending stress. End notches fall in the middle, 1/4, because the ends carry low bending stress compared to the span. Let me give you the complete rules so nothing is missing. For bored holes, maximum diameter is 1/3 of the actual depth. No hole may be located within 2 inches of the top or bottom face of the joist. No hole may be within 2 inches of any other hole or notch in the same member. And here is a critical distinction that official preparation resources consistently highlight. Holes are permitted in the middle, 1/3 of the span. The middle third prohibition applies to notches only. A bored hole within the size and clearance limits can be placed anywhere along the span. Many candidates miss this distinction and lose points because of it. For span notches, maximum depth is 1/6 of the actual depth, and this applies only in the outer thirds of the span, never the middle third. The horizontal length of any notch must not exceed 1/3 of the joist's actual depth. And I will add this because experienced framers know it, and the code supports it. Square or rectangular cutouts are not recommended. Square corners concentrate stress at precisely the point where the notch begins and are where cracks initiate under repeated loading. Angled cuts distribute that stress transition more gradually. For end notches, maximum depth is 1/4 of the actual depth at the bearing point only. And the rule that completes this section: no holes and notches may occupy the same cross-section in a member. Measured horizontally along the span, they must be separated by at least 2 inches. I put a chart up for you here, showing every floor joist and rafter rule in one place, the rule type, the maximum limit, and where along the span each applies. Look at the middle third row. It reads 0, prohibited, not a smaller fraction, 0. That is what makes it the most testable concept in this entire section. Nominal versus actual dimensions, the math trap. This is the single most common source of mathematical errors I see on this topic, and it is entirely avoidable once you know one simple fact. The fractions I just gave you, 1/3, 1/6, 1/4, are applied to the actual depth of the lumber, not the nominal size printed on the material tag. A 2x10 joist does not measure 10 inches deep. When softwood lumber is surfaced and dried at the mill, it loses material from all 4 faces. The nominal size is a legacy label from the era when lumber was sold in rough-cut dimensions before surfacing. The actual surface dimensions are fixed by industry standard and do not vary. Here are the 5 numbers you need to memorize. A 2x4 is 3½ inches actual width. A 2x6 is 5½ inches actual depth. A 2x8 is 7¼ inches actual depth. A 2x10 is 9 1/4 inches actual depth. A 2x12 is 11 1/4 inches actual depth. The process for any calculation is exactly 2 steps. Step 1. Identify the actual dimension. Step 2. Apply the fraction. Let me walk through 3 examples so this process is automatic. Maximum bored hole diameter in a 2x10 floor joist. Actual depth is 9 1/4 inches. 1/3 of 9 1/4 is approximately 3 1/16 inches. Maximum span notch depth in a 2x8 joist. Actual depth is 7 1/4 inches. 1/6 of 7 1/4 is approximately 1 3/16 inches. Maximum end notch on a 2x12 rafter. Actual depth is 11 1/4 inches. 1/4 of 11 1/4 is approximately 2 13/16 inches. If you start with the nominal number 10, 8, 12, your result will not match any correct answer choice. That failure is by design. The exam assumes you know the actual dimensions of dimensional lumber. Commit those 5 numbers to memory before you sit down for the test. Engineered wood products, the exception that overrides everything. Everything I have told you so far applies to solid sawn lumber only. California Residential Code R502.8.2 draws a hard boundary. The solid lumber rules do not apply to engineered wood products. Engineered wood products include I-joists, laminated veneer lumber, LVL, structural composite lumber, glue laminated beams known as glulam, and prefabricated roof trusses. The code is explicit. Cuts, notches, and holes bored in these members are prohibited except where permitted by the manufacturer's recommendations, or where the effects of those alterations have been specifically considered in the design by a registered design professional. No 1/3, no 1/6, no percentage, no field judgment call. The only basis for any penetration of an engineered wood member is written documentation from the manufacturer's engineering specifications or from a licensed structural engineer who has evaluated that specific application in that specific building. Why does this distinction exist? Take an I-joist as the clearest example. An I-joist is not a solid rectangle of wood. It consists of 2 horizontal flanges, one at the top, one at the bottom, connected by a thin vertical web in the center. The flanges carry the bending load. The web carries shear. This geometry is fundamentally different from a solid rectangular timber, and the fractions derived from solid sawn mechanics have no engineering basis when applied to it. Notch through a flange and you have destroyed the element doing the primary structural work. The structural behavior of that member after such a modification cannot be predicted from any field fraction. It requires the manufacturer's engineering analysis. On a job site, this rule means one thing. The moment a plumber or electrician reaches for a tool to penetrate any manufactured joist, truss, or beam, you stop that work until the written penetration authorization is in hand. Your license attaches to what happens in that floor or ceiling assembly after you sign off on it. The memory anchor. Manufactured members require manufacturer authorization. The moment a member came from a factory rather than a timber yard, the field fractions are suspended. No written permission means no penetration. Full stop. Bearing and exterior wall studs. California Residential Code R802.8.2 divides walls into 2 categories with intentionally different rules because the structural forces acting on them are different. For exterior walls and load-bearing partitions, walls that carry structural loads from the floor or roof system above, the maximum allowable notch depth is 25% of the stud's width. Note the dimension, width, not depth. For a standard 2x4, the actual width is 3 1/2 inches. 25% of 3 1/2 inches is 7/8 of an inch. That is the maximum notch a plumber or electrician is permitted to cut into a bearing wall stud. Less than 1 inch. The code is deliberately conservative here because a bearing stud is actively carrying compressive load, and the risk of buckling increases with every fraction of cross-section removed. For bored holes in bearing and exterior wall studs, the standard maximum diameter is 40% of the stud's width. For a 2x4, that is approximately 1 3/8 inches. The edge of any bored hole must be no closer than 5/8 of an inch to the edge of the stud. This 5/8 inch clearance prevents splitting along the wood grain, a failure mode specific to holes drilled too close to the face of a vertical member. The grain runs the length of the stud, and a hole near the edge can cause a longitudinal split that propagates underload. There is an exception for larger holes. When routing a large pipe or duct requires a hole up to 60% of the stud width in a bearing or exterior wall, this is permitted, but only if the stud is doubled. The affected stud must be paired with a full height adjacent stud, creating a built-up column that compensates for the structural capacity lost to the large penetration. Additionally, no more than 2 successive doubled studs in a row may be bored this way. The doubling requirement is not optional, and it is not a recommendation. It is the condition that makes the larger hole permissible at all. One rule that applies to all wall studs, regardless of category. A bored hole and a notch cannot be placed at the same cross-section. They must be at different heights along the stud. Look at this chart, bearing wall rules on the left, non-bearing on the right. The contrast between 25% and 40% for notches and 40% versus 60% for standard holes is a direct focus area in official CSLB preparation materials. Those 4 percentages need to come to you without hesitation. Non-bearing partition walls, the relaxed rules. Interior non-bearing partitions. The walls that divide rooms but carry no structural load from the floor or roof system above operate under the same code section, but with substantially more permissive limits. For non-bearing partition studs, the maximum notch depth is 40% of the stud's width. For a 2x4, 40% of 3 1/2 inches is approximately 1 2/5 inches. That is more than twice the limit permitted in a bearing wall stud. For holes, the maximum diameter is 60% of the stud width, with no requirement to double the stud. For a 2x4, 60% of 3 1/2 inches is approximately 2 1/10 inches. The 5/8 inch edge clearance still applies in non-bearing walls. The prohibition against holes and notches at the same cross-section still applies. Those two requirements do not relax, regardless of wall type. The logic is direct. A non-bearing stud carries only its own weight and the drywall attached to it. The compressive stress in that stud is a small fraction of what a bearing stud carries, so the code extends proportionally more latitude for modifications. As the general contractor overseeing a multi-trade project, your critical skill is recognizing the instant a subcontractor crosses from a non-bearing partition into an exterior or bearing wall, because the rules change completely with that transition. Top plate cutting, the metal tie rule. The double top plate at the head of a load-bearing wall does a specific structural job. It ties all the individual studs together and distributes the loads from the diaphragm above evenly into each stud below. Think of it as the bridge between the structure above and the columns below. When a plumber or HVAC technician must cut through that plate to route a large pipe or duct, they are cutting the bridge. California Residential Code R602.8.2 addresses exactly this situation. When cutting, drilling, or notching of the top plate exceeds 50% of its width, a galvanized metal tie must be installed across the cut. The specifications are precise. The tie must be no less than 16 gauge in thickness, approximately 0.054 inches. It must be at least 1 1/2 inches wide. It must be fastened with no fewer than 8 16-penny nails on each side of the opening, and it must extend at least 6 inches past the opening on each side of the cut. There is one exception. If the entire side of the wall containing the cut is covered by wood structural panel sheathing, the metal tie is not required. The sheathing itself restores the structural continuity of the plate across the cut by providing a continuous lateral connection. The trigger is 50% of the plate width. A cut at 49% requires no corrective action under this provision. A cut at 51% triggers the full metal tie specification. Read the percentage in any scenario carefully before committing to an answer. My memory anchor for this rule is 16, 1 1/2, 8. The gauge, the width, and the nail count per side. And the trigger, 50%, roof rafters, same fractions, same logic. Solid sawn roof rafters follow California Residential Code R802.7 and R802.7.1, and the rules are structurally identical to floor joists. That is not a coincidence. The physics are identical. A rafter spanning from ridge board to wall plate is a beam under bending and shear, the same failure modes, the same distribution of internal stress, and therefore the same governing fractions. 1/3 of the actual depth, maximum diameter for any bored hole. 1/6 of the actual depth, maximum span notch depth in the outer thirds of the rafter. 1/4 of the actual depth, maximum end notch depth at the bearing point. No notches in the middle 1/3 of the span. 2 inches minimum clearance from any bored hole to the top or bottom edge. No holes and notches at the same cross-section. The bird's mouth, the combined seat and plumb cut where a rafter rests on the top plate, is an end notch. Its depth is governed by 1/4 of the rafter's actual depth. Inspectors verify this on every framing inspection. The calculation is the same process as every other end notch. Identify the actual depth of the rafter, divide by 4. Engineered roof members, prefabricated trusses, I-rafters, glulam ridge beams, follow R802.7.2. No cuts, notches, or holes without explicit manufacturer authorization or structural engineer approval. Same rule, same boundary, same reason. Complete reference matrix. I want to read through this chart with you so every number is in your ears as well as on screen, because the combination of visual and auditory reinforcement is significantly more effective than either one alone. Floor joists and rafters. 1/3 of actual depth for bored holes. 1/6 for span notches in the outer thirds. 1/4 for end notches at the bearing point. 2 inches minimum clearance from any hole to the top or bottom edge of the member. 0 notches in the middle, 1/3 of the span. No exceptions, no fractions, no conditions. Bearing and exterior wall studs. 25% maximum notch depth. 40% standard maximum hole diameter. 60% maximum hole if the stud is doubled with no more than 2 successive doubled studs. 5/8 inch minimum edge clearance for all holes. Holes and notches cannot share a cross-section. Non-bearing partition studs, 40% maximum notch depth. 60% maximum hole diameter with no doubling required. 5/8 inch edge clearance still applies. No holes and notches at the same cross-section. Top plate cut exceeding 50%, 16 gauge galvanized tie, 1 1/2 inches minimum width, 8 16-penny nails per side minimum, extending 6 inches past the opening each side. Exception if the full wall side is covered by wood structural panel sheathing. Engineered wood, I-joists, LVL, glulam, structural composite lumber, prefabricated trusses, no cuts, notches, or bored holes without written authorization from the manufacturer or a registered design professional. No fractions, no percentages, no field exceptions. Common exam traps, where candidates lose points. I want to walk through the 5 most consistent sources of error on this material, because knowing the correct rule is not sufficient if the question is engineered to steer you toward a plausible wrong answer. Trap 1 is nominal versus actual dimensions. A 2x10 is 9 1/4 inches deep, not 10. A 2x8 is 7 1/4, not 8. A 2x12 is 11 1/4, not 12. When a question names a nominal joist size and asks for a maximum hole or notch value, you must convert to actual depth before applying the fraction. Using the nominal number produces a calculated result that does not match any correct answer in the option set. That failure is by design. The exam is testing whether you know actual dimensions. Trap 2 is the middle third distinction between holes and notches. The absolute prohibition in the middle third of the span applies to notches only. Bored holes within the 1/3 diameter limit and the 2-inch edge clearance are permitted anywhere along the span, including the middle third. Many candidates treat the entire middle third as a no modification zone. It is not. Only notches are prohibited there. Trap 3 is the 60% hole requiring a doubled stud. If a question describes a hole exceeding 40% of the stud width in a bearing or exterior wall, Any answer choice that approves the whole without requiring a doubled stud is wrong. The 60% exception exists only in conjunction with the doubling requirement. They are inseparable. Trap 4 is applying solid lumber fractions to engineered products. Any question involving a manufactured I-joist, a prefabricated roof truss, a glulam member, or any structural composite lumber product does not use 1/3 or 1/6 as its governing standard. The only correct answer for any penetration of an engineered member involves manufacturer authorization or approval by a registered design professional. Trap 5 is the top plate trigger percentage. The metal tie requirement activates at 50% of the plate width, not 1/3, not 40%. A cut at 49% requires nothing under R802.8.2 A cut at 51% triggers the full specification. Read the exact percentage in the scenario before selecting an answer. Memory anchors. Lock every number. And let me give you the specific anchors I use, because this is a lot of numbers and they need to be accessible in under 3 seconds during a timed exam. For the 3 joist fractions, I use the sequence 3, 6, 4. Holes get the number 3, smallest denominator, largest fraction, most room. Span notches get 6, largest denominator, smallest fraction, least room. End notches get 4, the middle value, the middle situation. 3, 6, 4. Say that out loud right now. Say it again. Say it until it runs automatically without conscious thought, because that is the level of recall you need under exam pressure. For wall stud rules, bearing walls get the quarter, 25%, because they carry the most load and receive the tightest restriction. Non-bearing notches relax to 40%. Holes in bearing walls start at 40% and can only reach 60 with a doubled stud. Non-bearing holes go directly to 60 with no doubling. The pattern is tight for bearing, relaxed for non-bearing, and the 60% exception in bearing walls always requires the doubled stud. For engineered wood, manufactured members require manufacturer authorization. Every time, no fraction applies. The moment a framing member came from a factory, the only currency that matters is written permission. For the top plate, metal tie, 16, 1.5, 8. Gauge, width, nails per side. And the trigger is 50%. For the middle third prohibition, close your eyes for a moment and picture a floor joist under full load. The weight of a room full of furniture and people bearing down. The joist bowing imperceptibly at its center. The wood fibers at the top under maximum compression. The fibers at the bottom under maximum tension. That point at the center of the span is where the joist wants to fail. That is where it is working the hardest. That image is the rule. Burn it in. Every time someone asks about the middle third, see that image, and the answer is always 0. Before I let you go, I want to tell you about the audio practice quiz I put together specifically for this episode. Every question is read aloud. You tap your answer. You get instant feedback. No desk, no notebook, no screen you need to read. I built it specifically because I know how you are actually studying. Driving to a job site at 6 in the morning, sitting in a parking lot between calls, on a lunch break where you have 15 minutes and nowhere to sit down. That is the situation this quiz is designed for. Here is exactly how to find it. Go to the description below this video. You will see a link that says, Pass the CSLB. Tap it. It will take you straight there, directly to the quiz for this specific episode, not the general site. If anything I covered today is not completely locked in, the joist fractions, the stud percentages, the metal tie specification, the engineered wood exception, any of the exam traps, put your question in the comments below this video. I read every single one of them. Your questions directly shape what I go deeper on in upcoming episodes. And if you are not subscribed yet, I want to ask you directly, please subscribe. This exam covers a lot of ground, and there is an episode for every major domain. Framing, concrete, law and business, plumbing, electrical, Cal OSHA, estimating, all of it. Every episode adds another piece until the complete picture is in place. I'm going to take you through every testable area until you have everything you need to walk into that testing center and pass. Stay with me through every episode until you get your license. That is the plan, and I will be here for every step of it.